بسم الله الرحمن الرحيم. نبدأ المحاضرة. Gonna start the lecture for the wave properties lecture. The two major reference we are going to use is Applied Hydraulic Transient by Chaudhry, 2014, third edition, and also the Hydraulics of Pipeline System by LaRocque, Jepson, and Waters, year 2000. The pressure wave properties, the transient move as a pressure wave. The letter A is used to indicate the wave speed. Some of the books can use the letter C, but this is the only two letters you're gonna watch for them is A and C. But we're gonna use A in most of our lecture here. The wave speed depends on the fluid properties, pipe material, the joint, is it flexible or fixed, and the presence of dissolved gas, the percentage of the dissolved gas, the anchoring, the fixation of the pipeline. Assumption, it is used, we are going to calculate the wave speed for water without presence of free air, means undissolved gases in the form of bubbles. There is no bubbles here. Pipe has a thin internal wall thickness, which is D over E greater than 40. This criteria has been made by Waters 1984, and also in Streeter and Wiley he used D over E greater than 25. We're going to use D over E greater than 40 here. Pipe remains full of water during the transient events. No separation, i.e. there is no column separation that is generated, i.e. pressure is greater than the vapor pressure. Water has small air content, so that, as we all know, the water has some air content, so that magnitude of that wave speed may be assumed constant. The pressure is uniform across any section of the pipe, i.e. the inertial forces associated with the radial motion of the fluid are negligible. This has been made by the extended wave theory by Sokolov in 1955. Propagation of speed in elastic walls. We have learned that the rigid wave speed is the maximum speed of A is square root of K bulk modulus divided by rho. This is considered the rigid wave speed without any elasticity. And for the elastic, considering or taking care of the elasticity and the bulk modulus and the density in this general form, which we call it as A square root of K divided rho over 1 plus K f D over Young modulus E over A. The parameter as summary, the capital D here is the diameter of the pipe, E the thickness of the thin wall pipe, E is the bulk modulus of elasticity. Effective water compressibility has been taken care by the bulk modulus. Effective pipe elasticity has been taken care by the Young modulus of elasticity, the capital E. The wave speed calculation. In the wave speed calculation, we're going to use the same equation in the previous slide. Instead of, we have added a new parameter which is called psi, the Latin letter psi, which is this letter here. In the first table here, we can see the Young modulus of elasticity for the different material, different pipe material, of course, it's steel, copper, bronze, asbestos, PVC, and polyethylene. All this has been measured by the Pascal, 2.07 10 to the power 11 Pascal. If we're going to use a gigapascal, means that the number will be read as 207 multiplied by 10 to the power 9. Notice that the smallest number here is 0.8 gigapascal in the polyethylene. You can find this table in the LaRocque in the 2000, his book. Also, in addition that we are going to use water under atmospheric pressure 1 bar and the 20 degrees centigrade, where the bulk modulus of water will be measured as K equal 2.07 gigapascal. As we all know that the density of water at 4 degrees centigrade is rho equal to 1,000 kilogram per meter cube. In addition to that, we have a new parameter which is called the mu, which is the Poisson ratio. The Poisson ratio, it's a ratio between the transverse strain, which is epsilon t, and the longitudinal or axial strain, which is epsilon L, dividing each other, minus sign here. The Poisson ratio can be derived. And the table here is summarize the different parameters of Poisson ratio. As we noticed, that the highest one is a 0.46 for polyethylene. The smallest one in this table is fiberglass, which is 0.22. Wave speed. Again, it ranges between the 300 meter per second for PVC pipe up to the 1400 meter per second for steel pipe. Depends on fluid property, pipe material, longitudinal strain. The wave speed, again, this is the general form. K is a bulk modulus, rho is a density. All these parameters has been known. The new things here is the kind how we're going to fix the pipeline. For case A and case B and case C, the restraint and the C parameter here can be used 5.5 divided over 4 minus mu, 1 minus mu squared, and the 1 for the different cases of fixed, for one end, fixed, totally fixed, and flexible. In the next slide, we're going to elaborate in this a little bit to show the kind of fixation. And again, we put psi instead of C. Don't be confused here. In the case, there is 3 cases. Case number 1 is a pipe anchored at the upstream end. If we consider this is the reservoir, and this is the valve downstream, and this is the pipe. So the anchored at the upstream end only at the reservoir location. This is the equation we're going to use. And you can notice that 5/4 minus mu minus u. And the pipe in the second case, where pipe anchored against any axial movement. This is no movement along the axial direction at all. So there is a fixation here at the reservoir and fixation at the valve. And this is the equation. We can notice 1 minus mu squared here at the parameter. And the third one, we're going to use the same as case number 2 with having some longitudinal expansion joint here at the pipeline pass. So psi here we call in this form here. Again, this is for the general expression. Can use it for any thickness, but especially for thick wall, we need to use this one. Thick wall means if D/E less than 40, and you can find this in Waters again in 1984 book. Propagation speed of elastic wall. We have a reservoir, pipeline, valve. You can notice the fixation at the valve and fixation at the reservoir, the upstream. This can imitate the same fixation of case 2. It's pipe anchored against any axial movement. Example A, simple system composed by a reservoir at the upstream, steel pipeline, length L 4,800 meter, carrying water without presence of free air or gas. The valve downstream end. The pipe is anchored against any axial movement. This is case number 2, as we mentioned. The temperature is 4 degrees centigrade. So we have K as a bulk modulus, 2.07 gigapascal. Rho is 1,000 kilogram per meter cube. Young modulus for the steel, 207.7 gigapascal, and the diameter is 0.3 meter. E is 0.00755. If we put all these parameters and use case 2 from the previous slide, we're going to find out that psi is 0.9531 and the wave speed is 1225 meters per second. Again, to make it simple, people have made this chart for you. If you have d over e, in the previously, if I divide 0.3 as a diameter divided over 0.00755 meter, it's about 39.9. It's here. If I go vertical, going to the steel pipe, the dark blue line, you will find it's 1225, approximately the same answer. So chart is so easy to be used. If you don't have a calculator, you cannot calculate the wave speed. In addition, that all software now has this equation embedded, so it's better that you know how to calculate it properly and also how to read the chart for that. Another beautiful chart, you will find it in the literature. Here you will have a d over e, and you have Young modulus of elasticity for different pipe material. If we select d over e as a 40, which is this vertical line, and with steel pipeline, you will find out we are in the order of 1200 or 1225. If you are accurate in your calculation, you will find more or less the same answer of this value. Again, we have to mention that the wave velocity for varying air content is changing dramatically with the presence of air bubbles or the air content. If we divide it by volume of gas divided by the total volume of the liquid, total volume as a percentage, it means here, for example, if we take 0.1% of air content, you will find that the wave speed, instead of about 1200 meter per second, it will reach 600 meter per second. So this is, we have to take care of this value during our calculation. If we are studying a liquid with some high air content, we have to look for that. So this is a positive indication for the water hammer. This has been derived by Pressal 1965 in his famous paper there. Impact of transient. Joukowsky-Olivier equation, we call it Joukowsky or Olivier equation, estimate the transient pressure rise due to an instantaneous change in the momentum, which is delta H equal to minus A delta V over G. A is the wave speed, delta V is a change in the velocity, the G is the gravitational value of gravity. If A is 1000 meter per second, for example, in the concrete pipe, and the delta V is change of 1 meter per second, change from 1 meter to stop to 0, it means that it's minus 1. If you put minus 1 multiplying by 1000, multiplying by minus, it will be around 1000 divided by G, which is approximately 10. It will have a delta H of 100 meters. As we said, this is a huge increase in the pressure due to the small change on the velocity. Small change means we change it from 1 meter per second to 0. We stop the flow. Okay, so this is upsurge in the pressure head. As be aware, another things we have to be aware of is the thrust force, which is will result from that. The oscillation, the resonance. Resonance, you can find the resonance on the reservoir will amplified. Something will be amplified with time instead of decaying, the result of severe pressure oscillations here. But let's concentrate on the increase in the pressure, which is the Joukowsky pressure here. Characteristic time, another parameter we need to learn, which is called 2L over A. L is the length of the pipe. And then from the pump to the reservoir, or from the valve to the reservoir. Okay, so for example, if you have the pipeline at the reservoir, pipeline, and the valve. So the L, this is the length, L here. So if we say that characteristic time 2L over A, it means that the time we should take it from the wave to travel from the valve to the reservoir and back to the valve one more time, it's called 2L. Over A is the pressure wave speed, regardless if it is plastic, 300, if it is steel is 1400. So the characteristic time, which is 2L over A, it's a time required for a pulse or a wave to travel to far end, then return. Far end means travel from the initiation of the wave, which is a valve, for example, up to the tank and then back to the valve one more time. Sometimes it's a fraction of a second. If it is a short suction line, for example, it will be a tenth of a second for a force main, or it will be a minute for a long distance transmission line. Okay, everything is every category here has different attitude and different handling on the water hammer. System response to change. For example, so back here again, this is called the characteristic time for the system characteristic here. Again, system response to the change. The system response means if you initiate something that causes hammer, we compare this to the 2L over A. We compare the time of initiation or the time of movement of that things which make the hammer action, like valve movement. We compare it to the 2L over A. For example, valve movement, pump operation, for example, if it is zero time, if the response is zero, it means instantaneous. You mean you close the valve instantaneously. This is the zero time. We compare this to 2L over A, remember. If it is less than or equal to 2L over A, we consider it rapid and require elasticity. Elastic theory has to be used here. And then later we're going to learn the method of characteristics. If it is larger than 2L over A, we can call it gradual and can be solved by rigid column theory. If it is greater, much greater than 2L over A, it's a slow. Use rigid column theory or even the extended period of simulation. In our opinion, on the 0, on the 2, less than 2L over A or greater than 2L over A, we're going to use the elasticity here in our course. We're not going to use the rigid column theory. The only rigid column theory will be used and will be valid if we have much greater than 2L over A. Propagation speed. If we have an example like that, how long does it take for a pressure wave to travel 500 meters after a rapid valve closure in a 1 meter pipe diameter, 1 centimeter wall thickness, and steel pipeline? If I said steel, you go to the table, you will find that E is 200 gigapascal. If you consider the initial velocity 5 meters per second, for example, what will be the increase in the pressure? First, we have to calculate the wave speed. Knowing the Young modulus, the diameter, the wall thickness, we can calculate the wave speed, and then A is 2.2 gigapascal divided by 1000. 2.2 is a K bulk modulus divided by 200 for the Young modulus, and then the diameter divided by the thickness. We'll find that it is 1020 meters per second. If we have 1020 meters per second and we have 500 meter traveling distance, so L over A, what do you think the 500 meter divided by the wave speed, which is approximately, we can say it as 1000. If we divide 500 over 1000, it will be 0.5 seconds. So the time required here to travel along the 500 meter, it's 0.5 seconds only. You can notice how fast the traveling speed of this wave. If we try to calculate the increase of the pressure, which is delta H, which is equal to minus A delta V over J, we can use the same equation, which is A, which is 1020 meters per second, multiplied by minus 5 meters per second, minus 5 meters per second, which is a stop from 5 meters to 0. 0 minus 5 is minus 5. Divided by gravity, it will be 520. So delta P here is gamma H, gamma delta H. The rho is 1000, the G is 9.8, and the H is 520. We can find out that this is like the increase here is 5 megapascal or 52 bar or 740 pound per square inch. Again, a small exercise to show the difference between the closing time. It is just for the sake of showing to you that a sudden closure or a rapid closure or a slow closure, what will happen, the effect of Joukowsky pressure here. This is 30 meter water column, and this is 100 meter water column, 30. This is all Joukowsky pressure. This one will be slower, so it will be less than the 100 meter. Stress in the pipe hole. You can see the stresses in the pipe hole after calculating the pressure increase, the delta P due to the water hammer, which is the Joukowsky pressure, delta P بيساوي or when you calculate the delta H بيساوي minus A delta V على G, we can calculate the delta P of course, because delta P بيساوي gamma delta H. So we can say that the final pressure or the total pressure will be the initial pressure before valve closure, which is a steady state pressure P naught, plus the delta P, the increase in the pressure. We have two things to calculate here: the circumferential hoop stress, which is FC, which is sigma C equal P, which is the pressure, total pressure, multiplied by D over 2E, and then the longitudinal stress, which is FL, which is P by D square over 4 over by D, which is the perimeter. So sigma L, the longitudinal stress, will be PD over 4E. So we have two stresses to calculate here. This is the hoop stress, this is the longitudinal stress. Again, this is another exercise to be solved by you. I have put it for you here to exercise and then calculate using the same information. Again, we asked you to find out the FC and FL and delta P and delta H. This can be solved by you after the lecture. The most important thing is here is for the PVC pipe or the hoop stress versus cycles to failure. We have to know this information regarding the PVC or high density polyethylene pipe, that the more you use the pipe, the more you cycle the pipe on and off, or pump power failure and then return, and then power failure one more time, several times. It can be more than once in a day. It can be several times per day, and it makes the fatigue. This analysis has been done for using the hoop stress against the cycle to failure. This is the number of hours or number of cycle failure. We can notice that the stress can reach 1/3 after 100,000 cycles or 100 million cycle, for example. So the stress of the pipe, of the high density polyethylene pipe or the PVC pipe, has this disadvantage of failure or reduction of the stresses along with time or with using the pipe. Occasional and recurring pressure surge. It's another information we need to know when we study the hammer. Are we going to use surge occasionally or happen occasionally, or recurring? It's a repetitive. So occasional means immediate, short-term effect of the pressure surge event. Peak pressure surge caused by events outside the normal operation of the pipe, like pump power failure, the pump electricity is gone, so they're causing the tripping of all the system. Or we have recurring pressure surge, means it's on every day, more than once per day. Peak pressure surge caused by normal pipeline operation, like pumps turned off and on, or valve opening and closing several times a day, occurring at a frequency of more than once per day. Okay, let's concentrate on the short term. For example, during the short term, in considering the potential of short-term impact, we have an upsurge pressure increase, overpressure of the pipeline leading to pipe damage the system component, or another things can damage the pipe, also the downsurge. So the pipe can be collapsed due to the downsurge, or groundwater infiltration at leakage at the point, such as joint. So we need to look for both upsurge and downsurge. It's not only the high pressure, no, the low pressure also has an importance there. Peak, sir, identification of the peak. The maximum event over the course of the pipe design lifetime. When we look to the design, we need to see along the lifetime of the pipe design that it will sustain and it will be safe along the maximum event. So first in the analysis, as we previously, we can say, is it occasional or recurrent? So both of them is very important here. On the identification of peak surge, we need to look for the maximum event. It is not any event. When you design, you look to the maximum event along its lifetime. And you need to design that or you need to design that hammer or the protection you're going to use to resist the peak surge. Along that, we have two things. We have first, we have to look for example, in the velocity, we have to see what will be the maximum design velocity or the maximum anticipated water flow velocity along the pipeline. The worst case anticipated event along the pump strip is a power failure, for example. So we need to look for power failure action. If you look to the hydraulic transient and you look to a system like that, we need to look for the maximum pressure here. This is the most important parameter here for us to see if our pipe will sustain or be safe with this pressure or not. What are the maximum allowable pressure? It's another question here. So assume that you design the maximum severe pressure or the peak pressure along the pipeline according to the maximum velocity that will happen, according to the maximum power failure scenario that will happen. What will be the maximum allowable pressure along the pipeline? We all know the class rating of the pipe. For example, if I say the pressure class rating for the pipe is 10 bar, so this is the class rating for the pipe. So the pipeline shall have a pressure class rating greater than the static or working pressure in addition to the surge at any point in the system. So please put this in your mind. Your pressure class rating must be greater than the static or working pressure plus the surge at any point of the system. Maximum allowable pressure, again, we have this page which is by Carney. It is in the book of Water Supply System Analysis, selected topics. It will give you an indication of what will be the maximum incidental pressure you're gonna allow for your pipe. If you compare this with allowable maximum operating pressure over the allowable operating pressure. Allowable operating pressure, this is the operating pressure which you're gonna use, for example, 8 bar. I'm going to use a pipe allowable pressure for 8 bar. What would be the maximum allowable operating pressure for me? If the 8 bar is the allowable pressure will be, if I divide PMA, which is allowable maximum operating pressure, divided over the allowable operating pressure, which is PFA, if I divide it both together, they are equal here in the German guideline. So you cannot exceed the allowable operating pressure. As I said, if I buy a pipeline which has allowable operating pressure of 8 bar or 10 bar, so you cannot exceed more than the 10 bar. And if you are using the ASME code B31.4, so it will be allowed for you a 10% increase. If you European things is 15%, it's a British standard 20%, an Italian standard is 1.25 to 15% to 51.5%. In our design, we are going to use the one here at the German guideline. Again, I put an exercise for you to calculate the maximum allowable incidental pressure to show to you is it safe or not safe, and I put it in front of you so you can get that exercise and solve it. Thank you.